Hello students, welcome back again. In this part we will discuss about systems of SHM involved spring mass system. We will calculate time period of a spring mass system when they are connected in series or in parallel. Along with this we will calculate equivalent spring constant values. So let's begin. Let's begin with the topic system of SHM, and the special case we will discuss here is spring mass oscillation. So when any mass is connected with a spring and that spring executes simple harmonic motion, orientation can be horizontal, can be vertical. So this time we are talking about a vertical case, means a spring of constant K that is connected with a block of mass M. So in the first case we can see here, if there is a spring connected with a block, initially its weight is balanced by the spring force, that is K into X, equilibrium. On giving small external force, like we pulled it and just give it a small shear, what happens? It starts oscillating about the mean position. In that case, the previous case we discussed, that is mg should be equal to the force of the spring, that is equal to mg equal to K into X equilibrium. Third case, in this case, if we on providing some force or on providing sufficient motion to that system, it starts oscillation about the mean position. So X is the displacement gained by the spring on applying some force, and what restoring force is responsible to bring the system towards mean position. We have to calculate time period of that spring block system due to that restoring force in a vertical dimension. Now, we will write the force equation over here. Object of mass M is tied to the lower end of a spring constant K as shown in the figure. We have three figures A, B, C. When the object achieves an equilibrium, that equilibrium condition, the spring is destroyed by elongation x1. So we would like to calculate net force, that should be equal to 0. So force minus net weight is equal to 0, that is minus of kx is equal to weight. So we got F equal to minus of kx. So kx is just the force in the spring. Now the object is then pulled downwards to a distance x. On applying small jerk to the system, because we want to create oscillation into the system, and then release, what happens? It starts oscillation as discussed in part 3. We would like to draft the equation for that case. Force minus weight is equal to mass into restoring acceleration. So F1 is equal to Kx1 plus x, because weight value can be taken from this part. So on substituting, we get minus of Kx plus x minus of this value equal to Ma. So finally we get A equal to minus K by M into X, and we already wanted to prove this. If for any system, the acceleration should be a linear function of displacement in opposite direction, that is A equal to minus of X. That is what spring oscillation execute linear SHM. Now in the next slide we can see the case for horizontal motion. If there is an object of mass M connected with a spring of constant K and it executes, and O is the mean position, that is equilibrium position. So that is what extreme position, positive A displacement, and minus A is the leftist extreme. So we can discuss this case. If there is a block connected with a spring, already it is in the tied situation, it is in expanded situation at t equal to 0, that is in the extreme, that is at extreme position. When we released it, what happens? It would like to come to the mean position and then left extreme. It is mean, it is left extreme. Now it executes SHM about mean position having amplitude positive A and minus A. So what time changes from 0 to t by 4 to t by 2 to 3t by 4 to t? So we are getting A, M, and then direction of acceleration changes with respect to the acceleration. So we are getting Fs is equal to A in that case. So already we calculated force. Restoring force should be equal to mass into restoring acceleration. And we got the relationship as M equal to minus of Kx. And already we know that restoring force should be equal to the force in the spring. That should be minus of Kx according to Hooke's law. And acceleration is equal to minus k by m into x, and acceleration should be directly proportional to the linear function of displacement in the main equation, and that is a case of linear SHM. Also we can discuss the case of rotational angular SHM, means angular SHM, but we will carry on this part. That's why we got a is equal to minus k by m into x with a is equal to minus omega square into x. So we get omega square equal to k by m and omega is equal to t by 2. Therefore t equal to 2 pi into under root m by k. So like that. So the conditions for the spring mass system execute SHMs are: the elastic limit of the spring is not exceeded when the spring is being pulled. Means it should be in the elastic limit. If you apply force greater than that elastic limit, it will break. It will never come to the mean position. No significance of restoring force. So it should be in the elastic limit. Third part, a spring is light and obeys Hooke's law. So means force applied on a system should be directly proportional to the displacement in the spring within the elastic limit. Now, if we have a spring of length x initial and spring constant k, if we divide or spring into two parts, then what would be the spring constant? A spring constant will never change, it will remain same. Now, if initial case, if it is having potential energy u equal to 1 by 2 kx1 square, if we divide spring into two parts and then calculating their energy, so what elongation produced in case 1 is x1, elongation x2 and it is x3. So we will calculate total energy final, that is equal to 1 by 2 kx2 square plus 1 by 2 kx2 square. And if we want to know the difference of final energy and initial energy, so we will find a difference: 1 by 2 kx2 square plus 1 by 2 kx1 square minus kx2 square plus kx3 square by 2 minus 1 by 2 kx1 square. So we can discuss all these cases. And the last very important part, arrangement of a spring. If we have different arrangement, so always we have two types of arrangement: series and parallel. Series is what? Means one spring is connected with the another spring, and that is connected with a block. So we place these systems on, there is a mass K1, K2, K3. On providing it sufficient displacement to the spring, net elongation produced x net is equal to x1 plus x2 plus x3. And according to Hooke's law, we know that because force is common overall, so that should be equal to force upon k net. That should be equal to F upon k1 plus F upon k2 plus F upon k3. On solving this mathematical relation, we got 1 upon k equivalent should be equal to 1 upon k1 plus 1 upon k2, and these are the case of spring connected in series, as we can see. But this is a case of parallel. That is a case of parallel that we will discuss this part in the next slide. So whenever we have a systems of a spring in series or either in parallel, and we want to know their time period, so always keep in mind t should be equal to 2 pi under root of m upon k effective. Now, in the next part, we would like to discuss when springs are connected in parallel. So we have two different cases, case 1, case 2. We know that when two springs, both the springs are connected with a block of mass m. Same here, when the two springs are connected with a block of mass m, extension produced in one spring should be equal to extension or compression produced in the second spring. If extension produced in both the springs are same, we can say. So we can say then if we apply certain force to that system, so F external should be equal to Fr1 plus Fr2. So we are getting Fr should be equal to Fr1, F external should be equal to Fr1 plus Fr2. Restoring in one case, one spring, plus restoring in another case. So we are getting K into X because elongation produced in both the spring, because elongation or means we are talking about displacement, whether it is elongation or compression in the system. So it should be same. As in the part B, we are knowing elongation produced in one spring should be equal to compression in another spring. That's why we are getting K equivalent into X should be equal to K1X plus K2X. That's why we are getting K equal to K1 plus K2. And we want to know their time period, that should be equal to 2 pi under root of m upon K equivalent. Always we will proceed in this way. Now, we can also use the energy method to find out the net equivalent relationship. Total energy means total energy before the oscillation and total energy after the oscillation. So that is what 1 by 2 k1 x1 square plus 1 by 2 k x2 square should be equal to 1 by 2 k net x1 x is net square. On solving this mathematical lesson, we are getting k net is equal to x1 k1 plus k2. And there are different cases for which we can, like we would like to discuss. There is a rod, and yeah, in this way, if this arrangement execute SHM about mean position, so what we have to find whether these two systems are connected in series or parallel. Actually, this is a different case. Means this K1 will provide torque T1 and K2 will provide torque T2. Elongation produced in one spring will not be equal to compression produced, because we know that displacement above the circumference is different, or just half or just double the value of elongation produced due to elongation when the spring connected at center, because we know that angle formed at center is double always angle formed at circumference. So we know that arc is equal to angle into radius. So what we want to know arc relationship. When the angle is double, definitely they would be in relationship. So elongation means if K1 is compressed by x, the extension produced in K2 will be x by 2, like that. Also we have different cases, like a spring connected with a pulley and it execute SHM, and there is a pulley of mass m. So we can find out SHM for that case. Also we have a pulley connected with a spring, and then we are just applying certain force to that system. We have to find out the time period of both the system. So always we have to do three methods. Three steps. First step, apply the force at equilibrium. Weight should be equal to the net elongation in the spring. Second part, apply certain force to give it, or just apply some force to give it a small jerk, and it will start executing about the mean position. So we will calculate net force after elongation minus, we will write the equation. So restoring force should be equal to the net force, and in this way we will proceed the relationship. Or either we can use energy method. But if we have more than one spring connected, so we should understand elongation or compression produced in one spring should be connected with elongation or compression produced in another spring. Maybe double, maybe same, maybe half. So we must be aware with those relationships in different types of question. Now we would have a question now. A mass m at the end of a spring vibrates about the frequency, this one. When an additional mass of 1.2 kg is added to the mass m, the frequency is 0.48 Hz. Calculate the value of f. So we know that f is equal to 1 upon 2 pi into m upon k. Sorry, we want to know time. So actually it is equal to t equal to 1 by f, that is equal to 2 pi under root of m by k. So for the first case we are given the frequency is 0.88. So we are getting frequency is inversely proportional to 1 upon under root of mass m. For the two cases we will calculate. So f1 upon f2 is equal to under root of m plus del m upon under root of m. That's why on substituting the value 0.88 upon f2, that should be equal to m plus delta m. So means frequency is also given. We have to find out the value of mass m. So f2 is equal to 0.48. Then it should be equal to m, that is given as 1.25 plus m delta m upon under root of 1.25. So mean we can say we are getting 0.88 upon 0.48. It should be equal to under root of 1.25 plus m upon under root of 1.25 m. So we will proceed this mathematical lesson. Finally we will get the value would be around 0.529 kilogram. Means I know this value, I already calculated this one on the base. That's why we are getting value would be around 0.529 kilogram. So what formula we use? frequency is just equal to 1 by t time period. In case of spring mass system, that is equal to 2 pi under root m by k, and we will compare these two relationships and we will get the answer as 0.5 to 9 kilogram. That should be the value of additional mass added to get the frequency of 0.48 Hz. In this part, we calculated systems of SHM, their time periods when a spring connected with a blow. I hope you are enjoying. In the next part, we will discuss about oscillation of an inductance and capacitance connected in series. Along with this, we will calculate time period for a hydrometry system along with an example. I hope you are enjoying physics, so stay tuned with us.